Okay, in this section, we will introduce a new concept, the angular dispersion. And actually, it's related to the temporal posture of our interest. So let's start with the relation between angular and the temporal dispersions and derive some critical temporal dispersion formulas. Then very interesting phenomenon, intensity from tilt, whenever there is angular dispersion. So what is angular dispersion? Let's look at this figure. You have a broadband signal. Okay, the gray one is the power spectrum. The central frequency, say, is omega 0, which is here. And assume at this central frequency, the corresponding wave vector, beta vector, is represented by the green arrow. Say it is along the direction of z-axis. Okay. And this is defined as the reference direction. Then, if at some higher frequency, say omega equals omega 1, the corresponding propagation direction is different, say represented by the blue arrow here, making an angle theta of omega 1 with respect to the reference direction, the green arrow. Then at the third frequency, omega equals omega 2, the propagation direction is also different, making another angle theta of omega 2 with respect to the reference. So different colors propagate along different directions. This is defined as angular dispersion, or frequency-dependent angle, frequency-dependent propagation direction. Okay. So how do we formulate angular dispersion? Actually, it's quite trivial. Just write down your propagation constant. Actually, it's a vector function, not just a scalar function anymore, right? Beta of omega equals the product of this one, okay? And then this is the absolute value of propagation constant. As we have known, the absolute value or magnitude of propagation constant should be equal to the index of refraction, n of omega, times wave number in vacuum, omega over c. This is always true. The difference is now, in addition to magnitude, you have projections on x and z directions. It follows this picture. The x component is proportional to sine of theta. The z component is proportional to cosine of theta. And remember, theta is not a constant. It's a function of frequency. Okay? So the second term here is a function of frequency. The arrows changes with direction as frequency changes. Okay. And this is equation sheet we will use. And you can know the meaning of n of omega means material dispersion, right? If you have material dispersion, n of omega is not a constant but a function of omega. And the theta of omega represents the new concept, angular dispersion. Whenever you have angular dispersion, different colors will propagate along different directions depending on the definition of theta. But here I want to emphasize angular dispersion is different from angular spreading. What is angular spreading? Roughly speaking, it means with this broadband signal, how wide the group of arrows will spread angularly. Okay. Say this number is delta theta. you can approximate delta theta by this first order formula, theta of omega 1 minus theta of omega 2 absolute value, right? 好，所以 angular spreading 描述的是我这个宽频讯号每一个 color 沿着不同的方向前进，把所有的可能考虑进来之后，这一束光在角度上到底散布了多少度 ？OK， 那估计的方法当然就是把最高频的角度减去最低频的角度相减去绝对值，大概就是这个 angular spreading。And the angular spreading can be approximated by first order derivative of theta of omega, okay, times the bandwidth delta big omega, which is shown here. The width of this power spectrum is the bandwidth. Okay, and then this is different from the angular dispersion. They are two different things. Any question? Now, to our surprise, angular dispersion will automatically transfer to temporal dispersion. Say we can write down the electric field as a function of x, z, and t. Here we assume there is no y dependence. Okay, this is z-axis, reference direction. This is x-axis, the transversal direction, and it's also a function of time. Okay, x, z, t. It is proportional to real part of the integration of this one. Could you justify why is that? Why the electric field can be always written as real part of this integral? Can you do that? Here I already highlight the blue color and the purple color, right? This one means sinusoidal wave at frequency omega. Omega equals omega 0 plus frequency detuning omega t, right? So this is a sinusoidal wave. How about this? This is plane wave, right? Propagating along the direction defined by beta of omega vector, right? So you have sinusoidal wave, you have plane wave together. It means monotonical plane wave, right? Time harmonic plane wave. And the integration means superposition. So this is the superposition of infinitely many sinusoidal plane waves. Each one is weighted by this complex number, big A of omega tilde. And by superposition, you can synthesize arbitrary electric field on the xy plane and along the time axis, right? Is it okay? 我们本来就是用这个数学模型来表达任何的pulse， 来就是把各种的这个旋波叠加。如果你只叠加旋波没有这一项，你叠加出来的就是没有空间分布的平面波 ，z propagation only。那你加了这一项就可以表达更丰富的 information， 就是我叠加出来的 pulse 不只有在时间上，然后空间上只是沿着 z 走，我这空间上也可以根据我的beta of omega来决定。Here we need to talk about angular dispersion, so this is necessary. Without this term, there is no angular dispersion. Every color propagates along z direction. There is no angular dispersion. Right? So this is necessary. Then let's check two spatial points. The first one is the origin, 0, 0, which is here. Okay. If you substitute x equals 0, z equals 0, then beta dot r should be 0 always. y, your position vector r is 0, 0. So no matter what is beta, the inner product is always 0. If this is 0, this term can be dropped, right? So your electric field becomes proportional to real part of a simpler formula. Here you can extract e to the j omega 0 t out of the integration because it's independent of omega tilde variable. All you have to integrate is a of omega tilde times e to the j omega tilde t. Okay, but you can see the terms within the red bracket is nothing but a of t, temporal envelope function. Okay, because this is inverse Fourier transform of big A function, right? So you got small a function in the time domain. So it means if you observe the electric field at the origin, what do you see? You can see a temporal envelope function, small a of t, which is inverse Fourier transform of big A of omega tilde, and with a carrier e to the j omega 0 t. In the frequency domain, it means maybe a power spectrum represented by the blue curve, and a constant spectral phase, assuming your big A function is a real function, there is no spectral phase. So this is the electric field you can observe at the origin. Then, if we move the observation point to here, 0, L, say a distance L after the origin along the reference direction, what can we have? When your position vector is 0, L, x equals 0, z equals L. The inner product between beta vector and the position vector should be this, right? Because the beta vector is borrowed from the formula in the previous page, equation sheet here. And when x equals 0, the contribution from this x projection is nullified, right? And when v equals L, the contribution from z component is L times cosine theta. Okay, so that's it. That's why the beta dot r, the inner product is this one. And say we define the entire thing as minus of spectral phase modulation function, psi of omega. Okay. Then, what is the electric field? Electric field at 0, L, and arbitrary time t is proportional to real part of, again, carrier can be extracted out of the integration. The integrand is, in addition to big A and e to the j omega tilde t, as we observed at the origin, there is an extra term, e to the j psi of omega, and the psi of omega is defined here. Okay. Then you can see the result should be real part of a new envelope function, a prime of t, times the carrier, where a prime of t is the inverse Fourier transform of a modulated spectrum, original spectrum big A, times the spectral phase modulation function, e to the j psi of omega. So represented here, the power spectrum does not change. But because of this term, beta dot r, in the presence of angular dispersion, beta dot r is no longer 0. So you will have a nonlinear function of spectral phase modulation. So of course, now you have been familiar with the impact, right? If this is a parabolic function, what happens? If the short pulse at the origin is transform limited, it becomes chirped when you move the observation point to 0, L. So that means if you scan the observation points along the reference direction, you will see the pulse becomes more and more strongly chirped. Okay? And it occurs whenever you have this one, angular dispersion. If you have zero angular dispersion, theta of omega is just constant zero, right? That is no angular dispersion. Then psi of omega becomes zero. This effect will not occur. So no matter how long you move the observation point, the pulse does not change. There is no extra chirp. But if you have angular dispersion, there is extra chirp. Okay, any question? 好，所以这一页讲的是其实还蛮有趣的。只要你有角度色散，就是不同的 color， 沿不同的方向前进，那么 input maybe 是一个 transform limited pulse， 沿着参考方向移动不同的距离，你观察到的 pulse 就有不同的 chirp。这不是从材料来的，这个纯粹是由角度色散来的。OK。Is it okay for you, or you feel very weird? But I can justify why it is natural later, right? In terms of mathematical analysis, it's like this. But I think always we need an intuitive picture. Okay. So this is the way we can justify the frequency-dependent pastance. Okay. Say you have angular dispersion, so beta of omega arrow points to different direction at different colors. Okay. Then how about the phase front? What is phase front? If you have a sinusoidal plane wave propagating along this direction, you can imagine the blue dashed lines can represent the phase fronts. Phase fronts means you have a sinusoidal wave. If you collect the peak set of points about peak together, it becomes a line, right? The next line, maybe the next line. So you have parallel lines represents the phase fronts. Okay. So if you observe the phase fronts, you can see at the origin, this phase front cuts through the origin. But if you move the observation point to 0L, the propagation distance required such that the same sinusoidal plane wave space front cuts through 0L is not L, but this distance, right? This is L times cosine theta of omega. Okay, so that means for a specific color, say frequency omega, the path length is not constant L, but a function of omega. Okay, the formula is L times cosine of theta of omega. 意思就是，只要你有角度色散呢，同样观察点从00移到0L，不同的 color 所需要贡献到同样这两个观察点，它的路径长是不一样的。其实这个路径长跟角度有关，角度又跟频率有关，所以路径长跟频率有关。That is the so-called frequency-dependent path length. In terms of variable omega, P as a function of omega equals n times L times cosine theta. Okay, here, material dispersion, n of omega is also taken into account. In terms of lambda, just change all the variables from omega to lambda. You got n of lambda times constant L times cosine of theta of lambda. Okay. These two are equations 4 and 5. Okay. then it becomes natural, right? If you have frequency-dependent past tense, you must have frequency-dependent phase accumulation. And that is the source of spectral phase modulation, right? Different frequencies will correspond to different phase accumulations after a fixed propagation distance. So it's a similar effect as material dispersion, right? 材料色散里面，你怎么会有 spectral phase modulation？ 因为不同的 color 有不同的折射率，虽然物理上的 past tense 是相同，但是折射率不同，累积的 phase 就不一样。这是你 material dispersion 造成 spectral phase modulation 的原因。Angular dispersion 呢，最后的效果是一样的，但是路径不同。它没有不同的频率有不同折射率这回事，但是它不同的频率因为沿着不同的方向前进，它贡献的物理上的 path 不同，它一样会累积不同的 phase， 最后造成 spectral phase modulation. So the results are the same, but due to different causes. So in terms of formulas, okay, you have seen this relation between omega and the lambda, first order derivative. You can relate first order derivative, second order derivative, third order derivative of past tense with respect to omega to past tense with respect to lambda. Okay. The higher the orders, the more terms you need to relate these two groups of formulas. Okay, any question? Okay, here I try to derive dispersion formulas by way of wavelength dependent past tense. P is a function of lambda. P means past tense. The angular dispersion induced spectral phase modulation is like this. Minus of wave number in vacuum, omega over c, times the frequency dependent past tense, P of omega. Is it okay for you? 相位就是 wave number 乘距，现在只是把距 generalize， 从 constant 距变成 wave frequency dependent past tense. That's it. Starting with the formula about group delay, tau g. The physical meaning of group delay is the time required by different colors to propagate over a certain distance. Okay, it's frequency dependent. And maybe as early as lesson 3, we have known group delay is defined as minus of first order derivative of your spectral phase modulation due to the Fourier transform theorem. 还记得吗？那时候不是说时间上的 shift 对应到频谱的 linear phase modulation， 就你怎么把 slope 取出来，一节为分就是。那万一我这个不是线性函数，我还是取一节为分，那我就会得到 function of frequency， 我只得到 constant。那是一个 delay as a function of frequency, named as group delay. Okay. And if you use this formula, okay, shown here, you can get this. The group delay formula is 1 over c, a constant, times past tense plus angular frequency times past tense derivative. Then you can change the variable from omega to lambda. So P of omega equals P of lambda. Omega becomes 2 pi c over lambda. Okay, well known. How about P prime of omega? You need the help from the previous slide, right? here, this one. P prime of omega is related to P prime lambda in this way. Just use this formula. Okay. After that, you got this, okay, and then you can simplify the terms. Eventually, you got this. Group delay formula is 1 over C times path length minus wavelength times path length derivative. Secondly, group delay dispersion formula, GDD formula, symbolized by dg. By definition, it's minus of second order derivative of spectral phase, because this is the derivative of group delay. So you got a further derivative, you got this. And similarly, if you use spectral phase modulation function here, you can arrive at this. And the blue one is the same as the previous case, represented by this one. The green one, you need help from the other formula in the previous page. If you use that, you can simplify the formula into this one. Just a constant times a single term, P double prime lambda. And we also know, if you only look at the first order term, GDD parameter dg is approximated by beta 2 times L. It's closely related to the GBD parameter beta 2. We will use it later. Third case, GBD parameter, you can refer to page 5 of this lesson. Big D is some constant times beta 2. Okay, you see beta 2 here. And if you use the previous result, beta 2, what is beta 2? Just divide big L by both sides of equality. So you can have this one over big L. Okay? And eventually you have this formula, the GBD parameter formula. Okay, so this is the final result, equation 6. So what have we done in this page? How G, dg, and big D are all physical parameters we have simplified. Okay, but previously we saw these formulas when there is material dispersion only. Here we are talking about the impact of angular dispersion, but still material dispersion is still taken into account, because P of omega or P of lambda can have n as a function of omega, the material dispersion. So you can regard these formulas as the generalizations of the old formulas. Previously, material dispersion only. Now, both material and angular dispersion are taken into account in these formulas. Okay. So that's the meaning of this page. Any question?不要迷失在这个一群公式里面。这些物理量我们都看过，只是以前是只在材料色散的时候出现。我们都推导出，在只有材料色散的时候，涛 G 的公式是什么 ，dg 的公式是什么 ，d 的公式是什么，我们都推过了。现在因为我有新的成分，角度色散进来，材料色散也没放弃，一起出现，那公式要怎么样？现在就告诉你。只要你能够表达 path length as a function of frequency， 这些物理量的公式就用这一页描述。但是 exact formula 还没有推出来，因为比如说 equation 6 this term is preserved p double prime lambda. I did not calculate what is p double prime of lambda yet. Right? I just leave it there. But in the future, if you can calculate P double prime lambda, you can know the formula about GBD parameter big D. in the presence of material and the angular dispersion. We will see that example shortly.